Hello friends, welcome back to the channel. Today we are going to solve an interesting thermodynamics numerical asked in IES 1998. This question is very important because it combines first law of thermodynamics, ideal gas relations and thermal efficiency of a cycle. If you understand this single problem clearly, many GATE, ESC and competitive exam questions become very easy. So let's start. Now we will look into the problem statement. An ideal cycle is shown in the figure. Its thermal efficiency is given by option A 1 minus of V3 by V1 minus 1 whole divided by P2 by P1 minus 1. Option B 1 minus of V3 by V1 minus 1 whole divided by gamma into P2 by P1 minus 1. Option C 1 minus of gamma into V3 minus V1 into P1 whole divided by P2 minus P1 into V1. Option D 1 minus of V3 minus V1 into P1 whole divided by gamma into P2 minus P1 into V1. Now look carefully at the PV diagram. 1 to 2 vertical line where volume is constant and pressure is being increased. Now remember, according to the ideal gas law, when volume is constant, temperature must increase when pressure increases. In order to increase more temperature, we got to add heat. Therefore, in this process, heat addition takes place. Now 2 to 3 curved line. As the relation PV to the power of gamma is equal to C represents adiabatic process. 3 to 1 is horizontal line where pressure is constant and volume has been decreased. Now remember, according to the ideal gas law, when pressure is constant, temperature must decrease when volume decreases. Therefore, if temperature decreases, then heat leaves the system, which means heat rejection takes place in 3 to 1. Now we will deeply dive into the process 3 to 1. So process 3 to 1 is a constant pressure heat rejection process. Okay, and the formula for heat rejection during the constant pressure process is heat rejection is equal to specific heat added during constant pressure process into highest temperature value minus lowest temperature value. So in process 3 to 1, heat rejection is Q3 to 1. Highest temperature value is T3. Lowest temperature value is T1 and specific heat added during constant pressure process is Cp. Therefore, the heat rejection during the constant pressure process 3 to 1 is given by Q3 to 1 is equal to Cp into T3 minus T1 and consider this one as equation 1. Now look carefully in equation 1. Equation 1 cannot be simplified, but some substitutions can be done. In equation 1, Cp value is constant, but T3 and T1 values are varying. So we can do substitutions for T3 or T1. Both holds same solving method. So here I will do substitution for T3. For that I will apply ideal gas law on process 3. We get P3V3 is equal to MR T3. Consider this one as equation 2. And again I will apply ideal gas law on process 1. We get P1V1 is equal to MR T1 and consider this one as equation 3. Now divide equation 2 and equation 3. We get P3V3 whole divided by P1V1 is equal to MR T3 whole divided by MR T1. Since this is a constant pressure process, therefore P3 and P1 are same and this is an ideal gas. Therefore, mass and gas constant for each process remains same. Hence, P3 and P1 gets cancelled and MR gets cancelled. So the next step will be V3 by V1 is equal to T3 by T1. Now bring this T1 to the LHS. We get T3 is equal to T1 into V3 by V1 and consider this one as equation 4. Now I have found the value of T3 and I will substitute this T3 in equation 1. So the next step will be Q3 to 1 is equal to Cp into T1 into V3 by V1 minus of T1. Now take T1 as common. So the next step will be Q3 to 1 is equal to Cp into T1 into V3 by V1 minus 1. So here V3 by V1 minus 1 is V3 minus V1 whole divided by V1. Because we are taking LCM for the terms V3 by V1 minus 1. So the answer will be V3 minus V1 whole divided by V1. So the next step will be Q3 to 1 is equal to Cp into T1 into V3 minus V1 whole divided by V1 and consider this one as equation 5. Equation 5 is nothing but the value of heat rejection during the constant pressure process 3 to 1. Now we will deeply dive into the process 1 to 2. So the process 1 to 2 is a constant volume heat addition process, and the formula for heat addition during the constant volume process is heat addition is equal to specific heat added during constant volume process into highest temperature value minus lowest temperature value. So in process 1 to 2, heat addition is Q1 to 2, highest temperature value is T2, lowest temperature value is T1, and specific heat added during constant volume process is CV. So the formula for heat addition during the constant volume process 1 to 2 is Q1 to 2 is equal to CV into T2 minus T1, and consider this one as equation 6. Now look carefully in equation 6. Equation 6 cannot be simplified, but some substitutions can be done. In equation 6, CV value is constant, but T2 and T1 values are varying. So we can do substitutions for T2 or T1. Both holds the same solving method. Now I will do substitution for T2. For that I will apply ideal gas law on process 1. We get P1 V1 is equal to M or T1, and consider this one as equation 7. And again I will apply ideal gas law on process 2. We get P2 V2 is equal to M or T2, and consider this one as equation 8. Now divide equation 7 and equation 8. We get P1 V1 whole divided by P2 V2 is equal to M or T1 whole divided by M or T2. Since this is a constant volume process, therefore V1 and V2 are same, and this is an ideal gas, therefore the mass and gas constant remain same for each process. Therefore in this equation V1 and V2, MR and MR gets cancelled. So the next step will be P1 by P2 is equal to T1 by T2. Now bring this T2 to the LHS and P1 by P2 to the RHS. We get T2 is equal to T1 into P2 by P1, and consider this one as equation 9. Now I have found the value of T2, and I will substitute this T2 in equation 6. We get Q1 to 2 is equal to CV into T1 into P2 by P1 minus of T1. Now we will take T1 as common. We get Q1 to 2 is equal to CV into T1 into P2 by P1 minus 1. So here P2 by P1 minus 1 is P2 minus P1 whole divided by P1. Because if we take LCM for P2 by P1 minus 1 is P2 minus P1 whole divided by P1. So the next step will be Q1 to 2 is equal to CV into T1 into P2 minus P1 whole divided by P1, and consider this one as equation 10. Equation 10 is nothing but the value of heat addition during the constant volume process 1 to 2. So we have found the values of heat addition and heat rejection. Now it is easy to find the value of thermal efficiency of the ideal cycle, which is taken as neta. We know the formula for thermal efficiency of the ideal cycle, which is neta is equal to 1 minus of heat rejection divided by heat addition. So in this ideal cycle, heat rejection is Q3 to 1 and heat addition is Q1 to 2. So the next step will be neta is equal to 1 minus of Q3 to 1 whole divided by Q1 to 2, and consider this one as equation 11. Now we will substitute equation 5 and equation 10 in equation 11. Equation 5 is nothing but the value of heat rejection, and equation 10 is nothing but the value of heat addition. By substituting these two values in equation 11, we get neta is equal to 1 minus of Cp into T1 into V3 minus V1 divided by V1 whole divided by Cv into T1 into P2 minus P1 divided by P1. So here T1 and T1 gets cancelled. So the next step will be neta is equal to 1 minus of Cp into V3 minus V1 divided by V1 whole divided by Cv into P2 minus P1 divided by P1. We know that Cp by Cv is gamma. Therefore, in this RHS we can rewrite Cp by Cv as gamma. So the next step will be neta is equal to 1 minus of gamma into V3 minus V1 divided by V1 whole divided by P2 minus P1 divided by P1. So here V3 minus V1 by V1 whole divided by P2 minus P1 by P1 is V3 minus V1 into P1 whole divided by P2 minus P1 into V1. Because we have applied algebraic formula A by B whole divided by C by D is equal to A into D whole divided by B into C. So the next step will be neta is equal to 1 minus of gamma into V3 minus V1 into P1 whole divided by P2 minus P1 into V1, and consider this one as equation 12. Equation 12 is the thermal efficiency of the ideal cycle, which means the answer for this question, and this value is seen in option C. So therefore the answer for this question is option C.